Hello guys, welcome to the next video about LLMs. By now we know what self-attention does, which means that each word in a sentence learns to focus on the others that matter most. But how does that actually happen inside the transformer? What's really going on with those mysterious letters as we discuss Q, K, V? Today we will unpack them completely, because once you understand queries, keys and values, you understand the brains of every modern LLM. Let us start simple. Take the sentence, the quick brown fox jumps over the lazy dog. Each token starts as a vector, basically the embedding, a list of numbers representing its meaning. But a transformer doesn't just care what each word is. It cares how every word relates to every other one. To do that, the model needs a way to compare tokens, basically to measure which words should influence each other. That's exactly what Q, K, and V are for. Imagine every word as a person in a room. Each word plays three roles. As a query, it asks, who should I listen to? As a key, it says, here is what I have to offer. As a value, it carries the actual message to share. Now each word looks around, compares its query with everyone else's key, and decides how much attention to give them. The result, every word ends up blending information from the ones that are the most relevant to it. That's a self-attention. Here is the challenge. Our model starts with just one vector per token. It's embedding. We need to turn that single vector into three specialized ones, Q, K, and V. We do that using learned weight matrices. Each token embedding, call it X for example, is multiplied by three different matrices. WQ to create queries what the token wants, WK to create keys what it offers, WV to create values what it contributes. Each transformer layer has its own separate Q, K, and V. So every layer learns a different way of seeing the relationships. Once we have all the queries and keys, the model measures how well each query aligns with each key. It does this with a simple dot product, a measure how similar two vectors are. We talked about it in the last video briefly. Now we want to talk as a simple example. If Fox has a strong query for jumps, their dot product will be large, meaning Fox attends strongly to jumps. These raw scores are scaled. We divide them by square root of vector size. Then we apply a softmax function so that all attention weights for a token sum to 1. The result is a smooth probability distribution, which is basically a map showing how much attention each word gives to the others. Let's visualize it with a sentence. The quick brown fox jumps. Each word attends differently. Fox gives high weight to jumps. Quick looks at brown and fox. If we plot those weights, we get an attention map, a heat map showing exactly where the model is focusing. That's how transformers build context. Now that we have attention weights, we use them to blend the value vectors. Each token output is a weighted sum of all the other tokens' value vectors. So when processing Fox, the model might mix information like this: 70% from jumps, 20% from quick, and 10% from brown. This blending gives every token a context-aware representation, a meaning shaped by entire sentence. And that's how a transformer understands. It doesn't memorize rules or grammar. It computes relationships. Every token becomes a mixture of others weighted by relevance. That is why transformers can capture long-distance dependencies, resolve pronouns, and maintain coherence across paragraphs. But here is the catch. A single attention pattern cannot capture everything. Sometimes we care about syntax, sometimes about the meaning, sometimes about long-distance cause and effect. So transformers use multiple attention heads. Each head has its own set of Q, K, and V projections, each learning to focus on a different type of relationship. Then all heads are concatenated and projected again, and with that each head is like a different expert looking at the sentence from its own perspective. Imagine reading a paragraph several times, once focusing on nouns, once focusing on verbs, once you may focus on emotional tone, and at the end you may focus on cause and effect. That's what exactly multi-head attention does automatically. Each head learns its own pattern of attention, and together they form layered understanding of meaning. The brilliance of Q, K, and V is that key enable dynamic computation. There's no fixed pathway. Every forward pass builds new connections based on the input sentence itself. That is why the same model can translate, summarize, and reason without changing its architecture. The attention mechanism is flexible enough to rewire itself on the fly. It can learn relationships dynamically as it reads. So for now, we have decoded the brain of the transformer, Q, K, and V, and how multiple heads think in parallel. But these attention layers don't work alone. They are wrapped inside a powerful structure that includes normalization, feed-forward layers, and residual connections. That's what we will explore next. If you like this content, don't forget to hit like button and also write your comments and questions in the comment section down below. If you want to continue this topic, don't forget to click on this video. Until the next video, good morning, good afternoon, and good evening. Bye.